He points to Gödel's incompleteness theorems, which prove that in any sufficiently complex mathematical system, there will always be true statements that cannot be proven within that system's own rules. Yet, human mathematicians can often perceive the truth of these unprovable statements through a flash of insight or understanding. This, for Penrose, is a critical clue. He argues that this ability to see mathematical truth beyond the confines of a formal system suggests that the human mind is not itself a formal system. If the brain were just a computer running an algorithm, it would be bound by the same Gödelian limits as any other machine. It would have its own set of unprovable truths that it could never access. But our capacity for genuine, flexible understanding points to something more. Penrose concludes that whatever consciousness is, it must be non-computable. It must harness some physical process that cannot be simulated by a standard digital computer, no matter how powerful. This is a bold and profound claim, as it seeks to place the mind outside the entire framework of modern computation. This objection fundamentally reframes the problem. Instead of asking what kind of computation creates consciousness, Penrose asks, what physical process in the universe is non-computable, and could the brain be using it? The answer, he believes, lies in the most mysterious and poorly understood corner of physics, the intersection of quantum mechanics and gravity. He proposes that the very act of consciousness is tied to the process by which the fuzzy, probabilistic world of quantum possibilities collapses into the single, concrete reality we experience. This isn't just a philosophical preference. It's a search for a physical mechanism that could explain the unique, non-algorithmic nature of human thought. This line of reasoning places Penrose at odds with the vast majority of neuroscientists and AI researchers. It suggests that the quest to build a conscious machine by simply writing more complex software is doomed to fail. If he is right, no algorithm, no matter how sophisticated, can ever achieve genuine understanding because it is playing a different game entirely. The brain isn't just processing information, it is tapping into the fundamental process of physical reality's creation. The search for consciousness, then, must leave the world of pure information and venture into the strange physical machinery operating at the quantum scale within our own neurons. The brain is to harness a non-computable quantum process. It needs a place for that process to occur. The conventional view of neurons, as simple on or off switches firing in a noisy, classical environment, just won't do. Quantum states are notoriously fragile. The slightest thermal vibration or interaction with the environment can destroy them in a process called decoherence. The warm, wet, and chaotic interior of a living cell seems like the last place one would expect to find delicate quantum effects at work. This is the warm, wet brain objection, and it is the single greatest challenge for any theory of quantum consciousness. A suitable location must be found that is somehow shielded from this environmental noise. This is where Stuart Hameroff, an anesthesiologist and consciousness researcher, enters the story. He proposed that the perfect candidates for hosting these quantum computations are the microtubules. These are tiny, cylindrical protein polymers that form the cytoskeleton or structural scaffolding of every cell, including neurons. For a long time, they were thought to be simple structural supports, like the girders in a building. But Hameroff argues they are far more sophisticated. He suggests they are information processing devices in their own right, acting as the nervous system within the neuron. Their hollow, crystalline structure and the materials they are made of, he claims, could create an environment isolated enough to protect quantum states from the chaos of the cell. Microtubules are built from small, peanut-shaped proteins called tubulin. Each tubulin protein can switch between at least 2 different shapes, driven by the location of tiny quantum particles within it, known as electrons. According to the theory developed by Penrose and Hameroff, orchestrated objective reduction, or ORCH-OR, these tubulin proteins can enter a quantum superposition, existing in both shapes at once. Furthermore, they propose that these individual superpositions can link up, becoming quantumly entangled with their neighbors along the microtubule. This would create a large coherent quantum state, a form of quantum computation unfolding within the very skeleton of the neuron, shielded from the noisy cellular environment. This is a radical reimagining of cellular biology. It elevates the microtubule from a passive structural element to the active computational core of the neuron. Instead of the neuron being a simple switch, it becomes a quantum computer, running complex calculations inside its own internal framework. Each neuron, in this view, is vastly more powerful than a simple bit in a digital computer. The brain is not just a network of 86 billion switches, but a network of 86 billion quantum processors, each containing countless quantum bits. This provides the necessary biological hardware for Penrose's non-computable process, setting the stage for the most crucial element of the theory, the role of gravity. Having proposed a location for quantum computation, the microtubules, OR needed a mechanism to connect this computation to conscious experience. This is where Penrose's core idea about quantum gravity comes into play. In standard quantum mechanics, the collapse of a superposition into a definite state is a major puzzle. It seems to happen whenever a quantum system is measured or observed, but what constitutes a measurement is not clearly defined. Penrose offers a radical solution. A measurement is not needed. Instead, gravity itself resolves the ambiguity. This proposed mechanism is called objective reduction, or OR, because it is an objective observer-independent process. The theory links quantum mechanics to Einstein's general relativity. According to Einstein, mass and energy curve the fabric of space-time. This curvature is what we feel as gravity. Penrose argues that when a particle is in a superposition of being in two places at once, it creates two slightly different curvatures in space-time. For a brief moment, space-time itself is in a superposition, a tiny blister of ambiguity. He posits that the universe does not tolerate this state of affairs for long. This separation of space-time from itself creates a gravitational self-energy, a kind of instability. When this energy reaches a critical threshold, the system becomes unstable and spontaneously collapses into one single definite state, with no measurement required. This leads to a beautiful and simple equation. Tau equals h bar divided by Eg.